Okay, let's get started. The first minute or two are non-essential, so it's okay if people are coming in. This is a new topic, propositional logic, and this is about making agents that know things. The way it fits into the outline of the course is pictured in this diagram I'll show you guys. So we can think about agents having an understanding of the world in three different ways. The most basic way is an atomic understanding of states of the world. And, well, actually, I'll fill in the details of this once I show you the other axes. So these are ways the agent can represent its knowledge about the world. These are different ways the world can be deterministic, everything follows fixed rules, or stochastic, there's some randomness involved. And the relationship of the agent to the environment can either be that the agent knows all the rules of the environment or doesn't. So we started with search. And search was applicable to known deterministic worlds. And the agent used an atomic representation of the state. So state 1 versus state 2, they're just names. There's no way of understanding the way they might relate to each other. There's no sense in which state 4 might be more similar to state 5 than to state 6. It's just a set of discrete states, and there's no internal structure. Now we're going to be talking about logic. And the first kind of logic we're going to be talking about, propositional logic, is going to deal with a factored representation of the world. So you can think of a factorization of the world state as representing the state of the world as a vector. And so you might think that states with vectors that are close to each other are more similar in some sense than states with vectors that are farther away from each other. Maybe you can do reasoning about whole vast sets of states that have similar factors. And then at the end of the logic section, we're going to be talking about first-order logic, which is an even richer, involves an even richer understanding of the world. And so structured, I'm not sure there's any conventional meaning to that that's very specific, but it's not just a vector. There's some other way of representing the state that is more expressive. And then, looking forward through the rest of the semester after logic, we're going to talk about Bayes nets, which are ways of understanding a stochastic world through a factored representation, provided that the world is known. Then we're going to be talking about MDPs, and this is going back to an atomic representation, but we're bringing in planning. And then finally, we'll get to reinforcement learning, which finally takes us into unknown environments. So that's just a bit of a roadmap of where we've been, where we're going. Okay. Logic. So we're going to start by talking about propositional logic. I can't remember. Is this there we go. And logic is a system by which you can write down a set of facts formally and understand what other facts follow from that. And for propositional logic in particular, so different kinds of logic have different kinds of syntax and semantics. So we're going to talk about the syntax and semantics for propositional logic, and then we're going to talk about how to apply that to a Pacworld example. And then with propositional logic established, we'll then talk about inference. And first we'll talk about inference via model checking. Then we'll talk about inference via theorem proving. Obviously, I'll explain. I'm not expecting you to know what those terms mean. We'll get into them later. And in your project, you'll be developing a Pac agent that uses propositional logic. And then finally, we'll get to first-order logic, which is much richer. OK, let's just step back from what we've done so far, thinking about agents, and just like look around you, look at the other agents in this room. Agents acquire knowledge through perception, learning, language. We know the effects of actions. That's a transition model. We know how the world affects our sensors. And we have knowledge about the current state of the world. These will sometimes be incomplete, but we have some knowledge that is quite general, that is not just this is what this state looks like and how it connects to this state and how it connects to this state. We can generalize better than that. And it allows us to keep track of a world we can only partially observe. It allows us to formulate plans to achieve goals. It allows us to do things like design and build gravitational wave detectors. Building the first gravitational wave detector involved an immense amount of inference from things we knew, from other things we observed, to their logical consequences. We could never have just stumbled our way into building a gravitational wave detector. We would have to understand the principles at play and how this new unvisited state out of a vast sea of states could possibly be one that we might be looking for. So for really complex things, it stands to reason that we will need to design agents that somehow know things. And what we're going to be talking about is a particular way of putting knowledge into agents. So for this section, what we'll mean by a knowledge base is a set of sentences in a formal language. Sentences in the set are considered to be true. So there's our knowledge base. And then, to build an agent, we're going to take a declarative approach, which means we tell the agent facts. We tell it what it needs to know, or we tell it how its sensors correspond to different facts, and then we show it things. And then we ask, well, or it can ask itself, we're asking it, whatever, same difference. It can ask itself what to do. And these answers should follow from the knowledge base and some description of what the goal is. So these agents can be viewed at the knowledge level, what they know, regardless of how they're implemented, which will allow us to write very general code and then apply it to the setting of an agent in a Pacworld. Yeah, that was what I was just saying. A single inference algorithm can answer any answerable question from this knowledge base, and it's a very general algorithm. So you have either your knowledge base, and then you have your inference engine that takes the knowledge base as input and then figures out, deduces various other facts. So in the knowledge base can be domain-specific facts, and in the inference engine is generic code. Okay, to explain to you exactly how propositional logic works, I'll have to tell you about the syntax and the semantics. So logic is a bunch of sentences, and so we need to know what sentences are allowed. And then we'll need to know what possible worlds there are, and then which sentences are true in which worlds. So we have sentences, possible worlds, and then a notion of truth or falsehood, truth or falsehood. And our function, which takes a sentence and a possible world, well, I'll have to explain to you how that function works. I'll have to explain to you the function that takes those two things, and then once you're equipped with that, you can decide which sentences are true in which possible worlds, and then which sentences entail other sentences. And I'll get to what that means in a second. So here are some sentences. This is just the sentence could be longer than this. This is just a symbol representing the sentence. Actually, before I get to that, I'll give you this example. That will maybe look more familiar to you. So here's an example of a sentence. X is greater than Y. And here are two possible worlds. A world, in the world of propositional logic, a world is an assignment of values to variables. A world is an assignment of values to variables. here's a world, here's our variables, here are the assignment of values to variables. That's kind of a, I don't know, the word world will not immediately inspire that understanding. So just memorize that, basically. For propositional logic, a world is an assignment of values to variables. And then, to evaluate whether the sentence is true in that world, we assign the variables their values according to the world, and then there's some simpler, then we have some understanding of how to check whether it's true. So, this sentence is true in this world, false in that world. Here's a much more abstract picture. We have some sentences. There's sentence alpha 1, which will look much longer than that. We're just referring to it shortly. And here are the possible worlds where it's true. Here are the possible worlds where it's false. Same for alpha 2, same for alpha 3. You can see here that alpha 2 and alpha 3 are negations of each other. So you can kind of see how if we're in a world where alpha 2 is true, we're not in a world where alpha 3 is true. If we're in a world where alpha 3 is true, we're not in a world where alpha 2 is true. So they can't both be true at the same time. Okay, propositional logic is the first kind of logic that we're going to cover. And the syntax looks something like this. We'll get into the details more in the next slide. And a possible world will look something like that. So these are Boolean variables. This should be familiar, I think, to everyone, given the prerequisites for this course. So we'll go through it fairly quickly. And you can represent this more compactly just by putting a 1 or a 0 for some ordering of the variables, indicating whether it's true or false. And the semantics have rules like this. So here's some symbol. For reasons that will become obvious, we'll call it the and symbol. This sentence is true if and only if, is true in a world if and only if alpha is true in that world and beta is true in that world. So we read this out as alpha and beta. More details to follow, but I'll briefly tell you a bit what first order logic is going to look like. This is read as for all x there exists a y such that p of x and y hold. And it's not the case that q of Joe, comma, f of x implies f of x equals f of y. Don't worry, we'll get to that later. I'm going to kind of just breeze through that until we actually get to first order logic. But possible worlds for first order logic are a bit more complicated than just assignments of values to variables. Another kind of logic that you might not have thought about as a kind of logic before are relational databases. So in a relational database, you might see entries like this. Ali and Bo are siblings. So that's the basic form for a sentence. That's the syntax. And then a possible world are certain objects existing, having certain relationships. And the semantics, the way you understand what the database means, is that if the sentence is in the database, it's true, and if it's not in the database, it's false. So if sibling Ali and Charlie is not in the database, then the way we're supposed to interpret that is that they are not siblings. So databases can't, or these kind of databases can't express disjunction, that is, either this or that. Can't express implication or universals. Universals are like the for all x has this property. But maybe you're familiar with SQL, a query language, and the way you query the database, you can kind of express something like first order logic. You can ask, like, do all examples where this is true, all examples for which this holds, also have the property that this holds, and so on. Some relational databases that exist out in the world and are used quite a bit are the Google Knowledge Graph, the Facebook network, and maybe you can estimate that if 30% of queries are answered by the Google Knowledge Graph, that might be considered an extremely profitable knowledge graph. Okay. The coolest thing you can do with logic is figure out new things that are entailed by things you already know. So entailment, we write like this. We say alpha entails beta, or beta follows from alpha, if and only if in every world where alpha is true, beta is also true. That is the definition of entailment. Another way of saying that, the alpha worlds, the worlds where alpha is true, is a subset of the beta worlds. And note the direction here because it can be a little unintuitive. Alpha entails beta if the models that satisfy alpha are a subset of the models that satisfy beta. So alpha is kind of a stronger sentence than beta because it entails it. And so maybe it's a little surprising that alpha corresponds to a smaller set, but smaller sets you can also think of as stronger. Smaller sets of possible world, they're more highly constraining what's going on. They tell you more about the world you might be in. So you have the stronger sentence alpha entailing the weaker sentence beta. So here's alpha 1, there's the set of possible worlds where it holds. Here's alpha 2, the set of possible worlds where it holds. Who can tell me whether alpha 2 entails alpha 1 or alpha 1 entails alpha 2? Just wait, I'll just wait 5 seconds. Which one entails the other? I'd like to see a few guesses out there. Yeah. Alpha 1 entails alpha 2. Can you explain that?
If alpha 2 is true,
Uh-huh.
we're in a world that is in alpha 2, then that doesn't guarantee that we're in alpha 1, because it's also alpha 1. If we're in alpha 1, that doesn't mean we're in alpha 1.
So alpha 2 is this world. If we're in a world that satisfies alpha 2, we're in that world.
I was looking at the dark.
Oh, sorry. Yeah, that was confusing. Right. The convention that I used here is that the bright world is the one where it's true. So yeah, so it's the other way around. If it were, yeah, obviously if you switch light and dark, it goes the other way. Yep. So alpha 2 entails alpha 1. So we can say, for example, that alpha 2 is standing in for the longer sentence, not Q and R and S and W, whereas alpha 1 is just the sentence not Q. And you can see how alpha 2 would be truer in fewer possible worlds than alpha 1. There's our subset relation. Okay, so that's entailment. And now we want to know how we can discover entailment. A proof is a demonstration of entailment between alpha and beta. To construct a proof, we will use an algorithm. And a sound proof algorithm has this property. Everything it claims to prove is, in fact, entailed. Here's a proof algorithm that is not sound. Yes, beta is entailed. No matter what beta you give me, no matter what alpha you give me, I'm just going to say, yep, it's entailed. That will obviously give you some false positives. It will claim to prove things that are not, in fact, entailed. A complete algorithm has the property that everything that is entailed can be proved. Here is a proof algorithm that is sound but not complete. No. No, it is not entailed. No matter what the input is, the proof algorithm just says, nope, I can't guarantee you that beta is entailed. That algorithm will certainly never claim to prove something when it is not entailed because it never claims to prove anything at all. So, ideally, we would like a proof algorithm to be both sound and complete. It only tells you that beta is entailed if that's correct, and it does tell you that beta is entailed if it is. So now we're gonna discuss over the next couple lectures 2 methods for constructing proofs, 2 methods for doing inference. The first one is model checking. And this is the most straightforward given the definition of entailment, even if it's not the one that we'll be most used to thinking about potentially. I mean, in past math classes when you've proven things, you haven't really done this. You've done something that looks more like theorem proving, which is the next method, but I'll get to that in a second. So model checking is you look at, let's say you want to decide whether A entails B. You look at every single possible world where A is true. And then in each of those possible worlds, you check whether B is true. And if it is, then it's entailed, and if it's not, then it's not. And in propositional logic, we have finitely many worlds, so this is doable. In first-order logic, it's not so easy. Maybe you remember the sentence x is less than y that I showed you a couple slides ago. Let's say you want to know whether x is less than y entails x is less than y plus 2. And let's say x and y can only be integers. Obviously, we all know that x is less than y does entail x is less than y plus 2. But how would you go about that with model checking? I mean, could you check every possible assignment of x and y? No, because there are infinitely many. So once you get to first-order logic or beyond, this becomes a lot less straightforward. But it's fine for propositional logic. Okay, the second method is theorem proving. We search for a sequence of proof steps. These are applications of inference rules that lead us from alpha to beta. So for example, if our sentence alpha is P and P implies Q, and the next slide is going to actually define all these symbols. If alpha is P and P implies Q, then we can infer Q. This is called modus ponens. And this should look pretty familiar to you guys. Okay, so here's the syntax for propositional logic. We're given a set of propositional symbols. These are our variables. We can have as many of them as we like, but we have a finite number. And the variables can either take values of true or false. So xi, one of these variables, on its own is a sentence. Another sentence, and now I'll get into an algebra from constructing other sentences from sentences that we know about. So if alpha is a sentence, then not alpha is a sentence. That's how you read that symbol. If alpha and beta are both sentences, then that's a sentence, and you pronounce it alpha and beta. Likewise for alpha or beta. Likewise for alpha implies beta. And likewise for alpha if and only if beta. And that's it. So not only to completely tell you about the rules of syntax for propositional logic, I need to tell you things that are sentences, and I also need to tell you things that aren't sentences. Nothing else is a sentence. You can obviously do these one after another, so you can have alpha and parentheses beta or gamma. So I haven't written parentheses here, but depending on the order in which you combine these, it's useful to write them down with parentheses so it's clear the order that you've put them together. Okay, that's the syntax. Now for the semantics. So M is a model which assigns values to variables. The values are true or false. How do we tell whether a sentence is true or false in propositional logic? Well, if alpha is just a symbol, like xi on the previous slide, then we just look to the model. The model will tell us whether it's true or false. That's our answer. We just read it out from the model. then not alpha is true in M, if and only if alpha is false in M. Makes sense. Alpha and beta is true in M, if and only if alpha is true in M, and beta is true in M. This is probably all seeming pretty basic, but this is how we have to define things to make sure we have a coherent notion of truth. Alpha or beta is defined exactly as you'd expect. This, alpha implies beta, is a little, can be a little less intuitive. Alpha implies beta is true in M, if and only if either alpha is false in M, or beta is true in M, or both. So I think the easiest way to think about this one, I mean, if you're going to ask, like, why is it defined this way? One answer is just, it is. This is the meaning we wanted to have. This is the symbol we chose for it. Implies is the English word we gave to it. Deal with it. Like, that's what it means. But why did we choose the word implies for this symbol? Why does that make a bit of sense? So imagine that someone told you alpha implies beta, and you didn't believe them. What would you have to demonstrate to them? You'd have to demonstrate, okay, well, here's a situation where alpha is true, but beta isn't. And then they'd go, oh, I guess that's right. So if you're going to demonstrate that alpha, that it's not the case that alpha implies beta, then it has to be that alpha is true and beta is false. So then the opposite of that, the situation where you can't contradict someone who says alpha implies beta, is that both of these are that either alpha is false or beta is true. If either of these hold, your attempt at contradicting them with a counterexample will fail. So that's why we use the word implies for this setting. Any questions about that? Okay. And then alpha, if and only if beta is true, if and only if alpha implies beta and beta implies alpha in our model. So that's how we take a model and a sentence and we return whether it's true or false. Sorry, so much louder. If we have a big complex sentence, then we work down from the highest level symbol. So this is sometimes called recursion over syntax. So here's our function for taking in a sentence and a model and returning true or false. If our sentence is very simple, if it's just a symbol, then we look up the symbol in the model. Done. If the highest level operation is not, then we strip away the not, we evaluate the sentence that's there, that's left on the same model, and then we flip the value at the end. So we kind of say, okay, it's going to be not whatever's coming next. Whatever's coming next is the sentence inside. Same for and. If the highest level is and, we do and we make sure both of these are true. Then we evaluate the same function on the left-hand side of the and on the right-hand side of the and so on for or and implies and if and only if. And so this is sometimes called recursion over syntax. Yes?
Previous slide, if you want to make an example from A implies B, I'm kind of confused. Can I say it's snowing implies that the car is red, but it's not snowing, so does that mean the car is red?
So if you have this, if you know that snow outside implies car is red, and it's not snowing outside, you can't infer anything, really. You can't put those two sentences together in any interesting way. So it's consistent either way with the car being red or not. Yeah?
Would it be more of like an exclusive or that implies, like if you have both be true, where it's like A is false and B is true?
So another way of writing the A implies B is, let me make sure I'm getting this right, B or not A. Those are equivalent. But that is an inclusive or and not an exclusive or. There might be some way of putting together something with an exclusive OR, but I think the most natural way is understanding alpha implies beta is equivalent to beta or not alpha. Any other questions, either for this slide or for previous ones? Okay. So here's an example sentence. P and not Q or R. Sorry about this stuff. Here is a model, a possible world, assignment of values to variables. P is true, Q is true, R is false, or just 1, 1, 0. So now how do we evaluate this? How do we evaluate the truth of this sentence given this model? Well, our highest order operator is an AND, so we go down here. Then we evaluate the left-hand side, and we evaluate the right-hand side. Okay, let's evaluate the left-hand side. The left-hand side is just P. Go back down here. If alpha is a symbol, yes, it's a symbol. We look up P in our model. P is true. Okay, so this one returned true. Now we go on to the right-hand side of the AND. We do this. The highest level operator is an OR. We go down to OR, and so on. Recursion over syntax, I think maybe given that example, you can see why it's called that. You go down the syntax tree from the highest level to the lowest level. They return back up. And I think if you did this, you'd end up with false or false, false or false evaluates to false, true and false evaluates to false. You can think that through while you are, here's the attendance code and the QR code for that. And I'll take any questions also while you're doing this, either specific questions about this or high-level, out-there questions about propositional logic and what I've told you so far. Yeah, so that was the implies symbol. And if you just wanted to, like, know enough to get going with, then what I would tell you is anytime you see alpha implies beta, replace it in your head with beta or not alpha. But suppose you want to understand a little bit more. Well, actually, yeah, I guess what more are you interested in understanding about the meaning of that symbol?
Why did you define the way that? How does it make sense to say that either alpha is true or beta is false?
Beta is true or alpha is not true. Yeah. So what we want from that symbol is we want to have the sentence alpha and alpha implies beta. We want that sentence to entail beta, right? I mean, that's what we're going for when we're defining this implies operator. That's where we're trying to get. And so now replace alpha implies beta with beta or not alpha. Sorry, it would be helpful to write this down. So we have, easier to type normal letters. We have alpha and A and A implies B, right? There's our sentence. If we replace A implies B with B or not A, well, it's not going to be not A because A is required. So it's not going to be this one, so it's going to be that one. This is going to be equivalent to B. Does that make sense? So that's why this is what we want A implies B to be equivalent to. Yeah, no problem. Whoops. All right. Okay. Any other questions? Yeah.
Can you briefly go over what you mean by
Yes. Now is a good time to do that. Where is it? Here we go. The possible worlds in which one is true is a subset of the possible worlds in which the other is true. The possible worlds in which alpha is true is a subset of the possible worlds in which beta is true. That means alpha entails beta. Okay. Okay, let's get to an example with the most important kind of world, Pacman. So, we're going to modify Pacman slightly. This is going to be partially observable Pacman. So Pacman knows the map. He knows where the walls are. Is that right? Does he know where the walls are? I think no. He knows he knows which locations exist. But all he perceives are whether there is a wall or not to his north, to his south, to his east, and to his west. So, what variables do we need to represent Pacman's knowledge in propositional logic? We need wall locations. So here is a Boolean variable, which means there is a wall at location 0, 0. There's our 0, 0 spot. And we need a Boolean variable that says whether there's a wall at 0, 1, and so on. So for n, we need n different symbols for n locations. Then we need to have Boolean variables corresponding to Pacman's percepts. Am I blocked to my west by a wall? Wait a minute. No, that's not going to quite cut it. Because while the walls stay put, the question of whether Pacman is blocked to his west by a wall will change over time. There's no sense of the variables in propositional logic changing value over time. There's no sense of time. What we need is variables corresponding to each time step. So we need a variable that says, is Pacman blocked to his west by a wall at time 0? Is Pacman blocked by a wall to his north at time 5? All of these need separate variables, which can be true or false. These subscripts here are for us to understand what these variables mean. But much as the different states in search are not treated as having any structure, no matter what we might name them, these different Boolean variables are treated as atomic by propositional logic. So it's not like reading out that these kind of have some deep connection between them. These are just our names for them, but in the propositional logic system, they don't have any other meaning. You can kind of see the inelegance of that, and in first order logic, we can fix that, but not yet. For now, we need separate variables for every wall location. We need separate variables for every time step for whether Pacman is blocked for every direction. And then we need Boolean variables for what Pacman's actions are at different times. So W0 is true if Pacman moves west at time 0. E0 is true if Pacman moves east at time 0 or attempts to move east. And we're keeping track of the number of symbols this is going to take given the size of our Pacworld. So this is order n plus t so far. Then Pacman needs to know his location. And his location also changes, so we can't just have a variable that says Pacman's at location 1, 3, because sometimes he is, sometimes he isn't, maybe. So this is a variable that says at time 0, Pacman is at location 0, 0. This is going to take nt symbols, because for every possible location at every possible time, we need a Boolean variable that says whether, yes or no, is Pacman there at that time. So how many possible worlds are there? well, n locations and t time steps, adding up everything from the previous slide. That's order nt variables. And that's 2 to the order nt possible worlds, because each variable can take the value of either true or false. Yikes. So if n is 200 different locations and 400 time steps, generously giving Pacman a chance to visit every location twice, that leads to about 10 to the 24,000 worlds. And note that each world is actually a complete history. A world is an assignment of values to all the variables, including, at 0, 0, 0, at 2, 4, 2. So that's going to tell you everything about where Pacman is at every possible time. But most of these histories are pretty weird. So here's a possible history that works, given what I've said so far. Time step 0, time step 1, time step 2, time step 3. At 0, 0, 0, true. At 0, 1, 0, true. At 0, at 1, 1, 1, false. I mean, these assignment of variables, you can write them down, and they'll give you a sort of nonsense history like that. So what we'll want to add eventually are rules that rule out, or sentences that rule out some of these possible worlds. But even so, there will be a lot of possible worlds. So let's give Pacman knowledge. Pacman's going to have a knowledge base, which you can either think of as a set of sentences or one giant sentence with a bunch of ands in it, like this sentence and this sentence and this sentence. And so we're going to add, I think it's easier to think about sets of sentences, though. We're going to add sentences to his knowledge base. So first, let's tell him where the walls are. That'll help him out. So here's our sentence saying where there are walls. Wall 0, 0 is true. Wall 0, wall 0, 0 and wall 0, 1 and wall 0, 2 is, this whole sentence is true, which will mean that each of these variables has to be true. What else should we tell Pacman about walls? What other sentence should we add to his knowledge base? We've told Pacman where there are walls. What else do we need to tell Pacman about walls? Yeah. Yes, we will need to tell him that eventually. There's something else we need to tell him about walls. Yeah. Yeah, these are all things we'll need to add information. I just particularly about where the walls are. There's one thing that's missing from here. Yeah. Yeah, exactly. So this, if in English I told you there are walls at all these locations, you would assume that there weren't walls at other locations, because if there were, I'd have told you so. But that's not how propositional logic works. In propositional logic, you have to also say there are no walls at the other locations. Otherwise, could be true or not true that there are walls everywhere else. What else should we tell Pacman? Well, let's make it a little harder for Pacman. Let's not tell him where he is. But let's tell him that he's somewhere. So we'll say at time step 0, either he's at 1, 1, or at 1, 2, or at 1, 3, or so on. This is an inclusive OR. So we also have to tell him that he's not in more than one place. Now, I hate this sentence because this is such a nice, concise way of saying it, and we have to write down every pair of locations and say it's not the case that he's at both of those locations. Now, luckily for you guys, when you're doing your Pacworld projects, you will not have to type in this sentence. You can write Python code that writes out the sentence for you. And it's kind of doing what first-order logic is going to be doing, your Python code, that is. Yeah, but I would invite you to hate this sentence as well. This is a sign that propositional logic is kind of weak, because that is really the only way to say that Pacman's only in one place. You have to talk about every pair of locations he could be and say he is not at both of those locations at once. Okay, more to add to Pac. Yep. So, if we had every triple in here instead of every pair, then it would be possible for him to be in 2 places at once. Is that right? Yeah. Then it would be possible for him to be 2 places at once as long as he's not in 3 places at once. So if you can't be in 2 places at once, you also can't be in 3 places at once. But if you can't be in 3 places at once, you might still be in 2 places at once. So this is more specific. This is what we need to say. Also, it wouldn't help. It would be even longer. So how do you use these symbols to say that? Yes, in first-order logic we can do that. We can say, for all pairs of locations, x and y, if x does not equal y, that implies that Pacman is not at location x and at location y. That's the way we'd say it in first-order logic. We'd make good use of the for all symbol, but the for all symbol isn't in here. So yes, there are formal languages people have written that allow you to say that, but this is not one of them. Yeah. There's a reason we're talking about it anyway. There's some advantages to propositional logic, namely that there are some really good solvers out there for finding possible worlds that satisfy a knowledge base. Okay. We've told Pacman, what have we told Pacman? We've told him about the map and the initial state. Now we need to tell him about what his sensors mean. So the general structure of the knowledge that we'll add to Pacman's knowledge base is going to be something like this. There's some percept variable at time t, if and only if something is true about the world. So Pacman perceives a wall to the west at time t, if and only if he is in location xy, and the wall is in location x minus 1, y. Again, we'd love to use first-order logic and use the for all symbol and quantify over x and y, but we're not ready for that yet. So we have to write something that looks like this. Pacman receives the blocked to the west sense, blocked to the west perception at time 0, if and only if one of the following of this list is true. So this is the or, so it's any of these. If either he's at 1, 1 and the wall's at 0, 1, or he's at 1, 2 and the wall's at 0, 2, or so on. It's actually not quite as bad as the sentence I was complaining about in the last slide, but it's not great. And if you're keeping track of the number of sentences, these are 4 T sentences, each of size order n. You really have to keep track of both the number of sentences and the size of them. If you were only keeping track of the number of sentences, you could just cheat by combining all the sentences into one with and symbols in between them. So this is kind of order nt in the number of symbols. Yeah. Well, you can write the program in Python, but you do need to write a program for it. So you take some program that would take a set of sentences with Boolean variables and the output of the program is supposed to be assignments to those Boolean variables so that all the sentences are true. And it's called a stat solver, but we'll get to that later. Mm-hmm. So we're not telling Pacman where he is. And so he's going to use these sensors plus his knowledge of the wall locations to determine where he is. So if we didn't tell him how his sensors connected to states of the world, then he'd get a sense, he'd get a perception, and it would entail nothing about his location. What this sentence is going to allow is he's going to say at time 0, oh, I notice I'm blocked to the west. I know there are walls at all these locations. So one of these things has to be true. Okay, which is it going to be? Oh, I must be on the left edge. For that kind of reasoning to work, we need to tell Pacman the meaning, the correspondence between his sense, his perception, and facts about the world. Otherwise, getting perceptions tell you nothing, and it's useless. Yeah. Yeah, I mean, like, my seeing that chair in this second, given that I saw it in the last second, isn't particularly helpful because I know that if I saw it in the last second, it's still there. But to be safe, we want to give the rules of perception in case there's something they're going to tell us about the world. Maybe it ends up that a perception is useless because we already knew everything that it tells us. But when we're writing the rules of Pac physics and Pacman's relation to it, it's helpful to write out what all the sensors mean, even if maybe some of them are not going to be necessary. Other questions? Yeah.
The reason you do this is in case things change, like ends going, as opposed to like telling Pacman where he is exactly.
Yeah, I mean, we could tell him where he is the whole time, but that might be hard if we're trying to figure out where he should be the whole time. So yeah, I guess as a rule, it's helpful to tell the system as much as you can, except in these toy settings where we're trying to learn something from the fact that not everything is told. So yeah, tell them, but in the real world, tell the system as much as you can, and it can infer what it has to. And note this sentence about what the sensor means is valid for any world, even if the walls were different. So in this world, we could have just said that blocked to the west means you're in one of these 3 locations. And that would work. But that's just a less general sentence. We'd have to rewrite it anytime it's in a different world, anytime the map is different. Okay, there's more to add to Pacman's knowledge base. The transition model. How does each state variable get its value at each point in time? So there were a few variables that were subscripted by the time step. And we need to say something about how they relate to each other. So for example, there's the location variables. Is Pacman at location 3.3 at time step 17? And the general format for writing the rules for state variables, that is values of variables that change over time, is according to this successor state axiom. So xt is true if and only if one of the following is true. xt minus 1 was true, and the action taken at t minus 1 didn't make it false, or xt minus 1 wasn't true, but then the action at t minus 1 made it true. Obviously, there's more to fill in about exactly how this works. So for Pacman's location, it gets a little messy. So here's how we'd write out the whole thing for describing what it takes for this to be true. Either he was at that location at time step 16, and he tried to move north but was blocked. He tried to move east but was blocked. He tried to move west but was blocked. He tried to move south but was blocked. Those would all be ways that he could have been there already and stayed there. Or he wasn't there. He was at this neighboring state, and he moved north and wasn't blocked. Or he was at this neighboring state, and he moved east and wasn't blocked, or so on. And it's messy, but it's still constant in length. Yeah? Yeah, so here is the first, the second, and there's a third and a fourth hiding in there. Yeah. There's a third and a fourth hiding in there also. That's because there are 4 actions. Yeah. Okay. So how many sentences have we given Pacman? The vast majority of this knowledge base is occupied by the order NT transition model sentences. Each is about 10 lines of text. And for n equals 200 locations, t equals 400 time steps, that's about 20,000 pages. So you definitely are going to want a Python program to write this knowledge base out for you. I wonder how long that would take to type if you didn't. And this is because, as I've been complaining about, this is because propositional logic has limited expressive power. We're not going to write that. We're going to generate them with code. In first-order logic, you only need kind of a constant number of transition model sentences. So, I'm going to skip this, actually. Maybe we come back to it later. Okay. There is a common confusion that I've heard has come up in past years, which is about the difference between entails and implies. So I've put in a slide about that. This is entails. This is how we write entails. Alpha entails beta. This is alpha implies beta. One of them is a well-formed sentence in propositional logic, and one is a fact about sets of models where sentences are true. Put up a 1 or a 2. Put up a 1 if you think this one means entails. Put up a 2 if you think this one is implies. Come on. Yeah. You can see by the color kind of too. But yeah, this is a sentence in propositional logic. This is a fact about sentences in propositional logic. So they're completely different things, but that's not very helpful. They do have some intuitive connection, and so I think the way to understand their distinction is to talk more precisely about how they are in fact connected, because intuitively they relate to each other very closely. So here's the connection. A knowledge base is a set of sentences, or you could call it one sentence with lots of ands between each sentence in the set. So if the sentence alpha implies beta is in our knowledge base, then if we add alpha to our knowledge base, that's going to entail beta. We're used to thinking about agents with knowledge bases, with things you can add stuff to. And so if I hear alpha implies beta and I add it to my knowledge base, then now, with respect to me, alpha kind of entails beta. I mean, technically I need to say alpha and my knowledge base entails beta, but we're used to kind of forgetting about that detail because we take the knowledge base for granted. So together with my knowledge base, alpha entails beta, if alpha implies beta is in my knowledge base. So that's the connection between the logical sentence alpha implies beta and the possibility of alpha entailing beta. So really, alpha doesn't entail beta on its own. Alpha entails beta once we also have the sentence alpha implies beta. And conversely, if you want to be able to put alpha into your knowledge base and get beta out, if you want alpha and knowledge base to entail beta, then it's a good idea to put alpha implies beta into your knowledge base. So that's the connection. That's the distinction. Any questions about how these are intuitively similar, how they're different, what's going on here? Okay. Remember, oh, yeah, question. The intuitive definition of entails is okay, well, let me just say the technical definition of entails first. Technical definition of entails is that for all possible worlds where alpha is true, beta is also true. So the technical definition deals with possible worlds or models. So the intuitive definition is if alpha is true, then beta is true, which is kind of the same as the intuitive definition of alpha implies beta. I mean, that's another way of saying why it's a bit tricky to remember what's the difference between these two things. So yeah, I mean, you asked for the intuitive definition, and I think, unfortunately, if you're only going off of intuitive definitions, you would define these two things in exactly the same way. If alpha's true, then beta's true. So you have to kind of get a little technical to tease apart what the difference is. Yeah? If, no, it doesn't. You have to add the, oh gosh, what's it called? There's some term for the left-hand side of an implication. You have to add that to your knowledge base as well, and then collectively it will entail it. So if this is in your knowledge base and alpha is in your knowledge base or added to, then these two together will entail beta. So alpha and alpha implies beta entails beta. But yeah, this is the way to think about it, I think. It's like adding that to your knowledge base will allow you to entail beta once you also add alpha to your knowledge base. Okay. So some reasoning tasks that we can do in Pacworld are, well, in any world, if we have the right propositional logic symbols to describe it and the right sentences to tell us how it works. The reasoning tasks we can do are, here's one, localization. If we have a map and local sensing, and this is the one this is the example we were looking at, given an initial knowledge base plus a sequence of percepts and actions, where am I? So it knows the map, doesn't know where it is, but it can perceive the world. It knows what those perceptions imply about the world, and it can deduce where it is. So that's one task you can do, you can use inference for. You can check to see if a given location is entailed by the knowledge base plus your sensors, plus your sensory information. Or we can do kind of the inverse of that. Let's say we know where we are, but we don't know the map. Given an initial knowledge base and a sequence of percepts and actions, what is the map? If I don't know where the walls are, but I know where I am, or I assume where I am even, then I see a wall here. Okay, there's a wall there. I move here. I see a wall, there's here and here. And as I move around and I sense new things, and I know where I started, I can build the map around me. And even better, we can do simultaneous localization and mapping. So given the same things as above, maybe you don't know either your location or the map, but as you get more sensory information, you can slowly start to build the map. SLAM, this is called, if I didn't say that already. And maybe most generally, most interestingly, we can do planning. Given the initial knowledge base, a sequence of perceptions and actions, what action sequence is guaranteed to reach a goal? So we can assert, in the Pacworld so far, there wasn't any mention of food or anything. So let's say the goal was just to get to the top right corner, or we have a more elaborate Pacworld. We can assert Pacman is at the goal state at 336 at time 6. What actions must have transpired in the middle, or what actions might have transpired in the middle? So that's how we can use logic to design agents that plan. They can do all these things at once. And they all use the same knowledge base and the same algorithm. Okay, I'm glad I added some of Thursday's slides to the end of this, because I think we're going to get to them. So let's just summarize what we've done up until now. Here is a new possible architecture for an agent. It is knowledge plus inference. Logic provides a formal way to encode knowledge as a set of sentences. The logic is defined by a syntax. What sentences are well-formed, or how can you put symbols together to make a well-formed sentence? How can you not put symbols together to make a well-formed sentence? What are the set of possible worlds, and what is the truth condition? How do we combine a possible world in a sentence and evaluate whether that sentence is true in that world? This is the recursion over syntax thing that we discussed. And a simple knowledge base for Pacman covers his initial state, the sensor model, what his sensors imply about the state of the world, and the transition model, how different state variables will change when he takes different actions. And then logical inference computes entailment relations among sentences, enabling a wide range of tasks to be solved. So we've talked about what entailment is, but we haven't talked yet about how you discover it, except briefly. One way of discovering entailment is enumerating every possible world where alpha is true, and then checking whether beta is true in all of those possible worlds. So that's one way. That's the only inference algorithm I've mentioned so far, and we'll see better ones soon. Let me pause here for questions about any of these 4 points. Mm-hmm.
So I go back to the difference between entailment and implies.
Yeah.
With entailment, is it kind of like it applies to possible world as opposed to implies just kind of like general probability between alpha and beta?
Yeah. Yeah. So entailment is a statement about the possible worlds that fit with a pair of sentences. And implies is one of the pieces of propositional logic that we can make other sentences from. You know, it can be part of a sentence. Okay, let's get a bit of a head start on the next topic. We're going to start with a simple theorem proving algorithm, a way of checking entailment in some settings. So here were our two forms of inference. There was model checking for every possible world. If alpha is true, make sure that beta is true in that possible world. And the second method, theorem proving, search for a sequence of proof steps I haven't really given you any sense of what those might be. Applications of inference rules, same, leading from alpha to beta. And a sound algorithm, everything that it claims to prove is in fact entailed. A complete algorithm, everything that is entailed can be proved. So if alpha entails beta, our algorithm will recognize that, and our algorithm won't tell us beta is entailed if it is not. So here is the forward chaining algorithm. And there are many well-formed sentences that do not play nice with forward chaining. So the syntax, there were whole way, you could have alpha and not beta implies gamma. That sentence is not, if that sentence is in our knowledge base, you can't use forward chaining unless you manage to rewrite the sentence into a different form. Forward chaining only works, and this is its main weakness, if the sentences in your knowledge base are of a particular form. But if they are, it runs really fast, so it's good to use. So pretty straightforwardly, I mean, if you really wanted to show it, you'd have to go back to the definitions of all these symbols. You'd have to write out truth tables for all possible values of all variables. But given that these have the meanings that we intuit, we're not going to go into that. If you have this sentence, x1 and x2 and so on and xn imply y, and it is in fact the case x1, it is in fact the case x2, and so on, then what we'd like to do is infer y. So forward chaining keeps applying this rule, adding new facts until nothing more can be added. So for the forward chaining algorithm to work, it requires the knowledge base to contain only definite clauses. Definite clauses are this kind of thing. A conjunction of symbols, conjunction means connected by ands. So x1 and x2 and x3 and so on implies symbol. This is, I mean, that is so much more restricted than general sentences in propositional logic. But there are certainly settings where we'll get sentences of that form. So here is, if all our sentences are this form, or if they are of the form single symbol, so a very simple sentence, it's just x is true, basically, then we can use the forward chaining algorithm. So this is what, this is the setting where this inference algorithm can produce entailed sentences. It can produce all entailed sentences, and it will only produce those sentences that are entailed. Yeah? Modus ponens, that's the Latin for that. It's the Latin for doing that step, really. It's for taking alpha together with alpha implies beta and realizing beta. And it's exciting enough to deserve its own name. Okay. The algorithm runs in linear time. That's so much better than the next algorithm I'm going to show you on Thursday. So that's the benefit from this simpler problem setting, is we can get an algorithm that runs in linear time. And the way it does that is we just use two simple tricks. We can go to a symbol and then get pointers to all the rules that it appears in. So each symbol knows which rules it appears in. And each rule keeps count of how many of its premises, that's the word, premises, are not yet satisfied. The premises are the things on the left-hand side of the implies symbol. This is the premise. This is the, again, I can't remember the word. It'll come up later. But you guys have to remember that word. Okay, each rule keeps track of how many of the premises are not yet satisfied. Here is the forward chaining algorithm. And here is a reminder about the sorts of clauses. I haven't told you what a clause is yet. You can think of them as, so a clause, a sentence is clause and other clause and other clause and other clause. Or if you're considering a knowledge base as just a set of sentences, you can say each sentence is a clause. So here's how the forward chaining algorithm works. It takes a knowledge base, it takes a query. It tells us whether that knowledge base entails that query. So this is a set of sentences, or one long sentence separated by ands, where each of the things we were calling a sentence we now call a clause. And Q is another sentence. So here is how it works. We'll go through this at the start of the next lecture too. I think 5 minutes is enough for it, but yeah, we'll do a review of it next time. So we keep count for each clause C. We keep count of the number of symbols in C's premise. So here we have X symbols in the premise of this clause. We keep track of which symbols we have inferred are true. And initially, we say that none of the symbols, we haven't inferred that any of the symbols are true yet. So we start with everything here initialized to false. So this is a table. And here's our agenda. It's a queue of symbols, starting out with only the symbols known to be true in the knowledge base. So recall the knowledge base contains clauses like this, and it also contains isolated symbols on their own. And if the symbol x5 is in our knowledge base, that means x5 is true. As long as our agenda is not empty, here's what we do. We take the first symbol in our agenda, remove it from the agenda, and do something with it. Our symbol P. Sorry, I said this was a sentence. It's actually just a symbol. I mean, that is a sentence, but it is a particular kind of sentence. We're checking to see whether this knowledge base entails the very simple sentence made up of only one symbol, Q. We're checking to see whether the knowledge base resolves the value of that variable. So if P equals Q, we're done. We have, the agenda is keeping track of symbols that we know are true, or things we have inferred are true. And so if Q is there, then we're good to go. Okay, if not, we keep going. If we hadn't yet inferred P, but now we have, because it's in our agenda, then we set inferred of P to true. So now we can recall later that we have inferred P. And for each clause in the knowledge base where P was in the premise, we remove the count. So basically, this clause, our program knows 6 different things are going to need to be satisfied before we can spit out Y. And as soon as we've inferred one of these things, now only 5 things need to be inferred before we can spit out the conclusion. So if the count has gone down to 0, then we add the conclusion to the agenda. So now you can see things are added to the agenda when we have inferred them. And you might worry, like, could we notice that x3 is true and then decrement our count twice because we've noticed x3 is true, x3 is in this clause, let's decrement our count? No, because once we've inferred it, we only decrement the count if we hadn't inferred it before, but we have inferred it now. So anytime we newly infer one of the symbols in the premise of this clause, we bring the count down. When the count gets down to 0, we have successfully inferred the conclusion, so we add it to the agenda. And then presumably, when we take it off of the agenda again, it will be newly inferred we can move forward with situations where y is in the premise. Yes. C is the clause. It's going to be something that looks like this, and our knowledge base is going to be a set of clauses. Okay, we're going to go over this at the start of the next lecture too. So you can stare at this for a little longer and come up with questions if you like, but don't worry if that was a little too rushed.